Very good. Good morning. My name is Druzdzel, and like you, I'm also an academic who spent 30-something years in academia. And then at some point, when close to my retirement, I'm retired, kind of early retirement, I started working for a company, Base Fusion, which we created with my business partner. The company is developing further and marketing and selling the software that we started developing at the university. The software is available for academic use free of charge. So any of you who wants to play with it, to use it, any teaching and research, academic teaching and research applications, you can use the academic version of the software. So what else can I tell about myself? I'm a Polish-born, studied in the Netherlands, did my PhD in US at Carnegie Mellon University, spent most of my academic life at the University of Pittsburgh, and now I'm a businessman, but an academic at heart, of course.
Happy to have you.
Today I'm going to tell you about three things, kind of three parts. The first two are going to be shorter. The third one is going to be a little longer. I'm going to briefly introduce to you Bayesian modeling, Bayesian inference. I suspect some of you have already you know what it is and have worked with it, so it's not something that is strange to you. Then Bayesian networks. And then learning Bayesian networks, causal discovery. I believe all three are going to be of interest to you. The first two are going to be somewhat theoretical, but really at the intuitive level. And we need a little bit of theory because you are academics, so you need to know what you are standing on before you start using the tools. So the first session, I think quite short, is going to be just an introduction to Bayesian modeling and inference. If you look at data, any measurements, and as engineers, as scientists, you are performing measurements, what you will notice is that data are very noisy. You see a male smoker who got cancer at 43. We have a female non-smoker who got cancer, but on the other hand, we have a female non-smoker who is 81, still perfectly healthy. So a lot of noise. This is not atypical at all. Data from any experiments, from any observations are noisy. And there are many reasons for the data being noisy. There are missing values, variables that you have never measured that essentially account for the noise or introduce more noise, many other things like errors in measurement, wrong information, errors, bad luck, etc. A beautiful quote from Benjamin Franklin. You must have heard the name. You've seen it on $100 bills. A politician, but also a thinker, and you could say also a scientist, interested in many things. Beautiful quote in a letter to a friend: "Nothing in this world is certain except for death and taxes." That means that all of us will die. I hope all of you who are younger than I will die later than I, but all of us will die. That's quite certain. And somebody will tax us. Wherever you live on earth, somebody will want money from us. Of course, that's an ironic way of saying that everything else is uncertain. Everything in life is uncertain. The uncertainty, just like we use arithmetics when we do shopping, we calculate 2 plus 2 is 4, and we don't pay too much at the counter, cash register, when we exit the supermarket, for example. Whenever we're dealing with uncertainty, we should use probability theory. That's the mathematical theory for processing uncertainty. If you depart from probability theory, you expose yourself to a so-called Dutch book. Dutch book is a bet that makes you guaranteed to lose. Almost like if you believe 2 plus 2 is 5, I can pump money out of you. How can I do that? I can offer you 2 times $2 and ask you 5 instead, because you believe 2 plus 2 is 5. And I can keep doing this until you are out of money. In the same way, if you violate any of the 3 axioms of probability theory, there is a proof that you are exposing yourself to a set of gambles, bets, that make you guaranteed to lose. Of course, if you are willing to act upon your convictions, some people have convictions, but they are not willing to act upon them. They just use their tongue. But if you are willing to stand behind your words, you are going to lose. Probability theory from your college, from your high school classes, you probably remember it as not that easy. There is for some people it may sound ironic, the quote from Laplace: the theory of probabilities is basically common sense reduced to calculus. It sounds perhaps ironic, but I assure you, after 30-something years working in this field, it's actually a very wise statement. At the intuitive level, probability theory is very easy to understand. It's the theorems, proofs, formulas that are quite complicated. But the intuition is quite easy. What is probability? Probability over an event, X. The event can be discrete. You can put a measure of uncertainty on the 2 outcomes of a coin toss. The event can be continuous, for example, body temperature. You can ask for a probability of the body temperature being above 38 degrees Celsius. You can also talk about distributions. In this slide, the most important thing is that any probability is conditioned on some background knowledge. And the same holds for models. If you build a model, it's always conditioned on something, our knowledge of the situation. We will not put it explicitly, but we need to remember that this is always the case. There's no probability that's kind of abstract. There's always some conditioning involved. The important thing is, this is really a rush review of the most important things. Joint probability distribution is, you can talk about probability distribution over a single variable, probability assignment to all the values of the variable, the domain of the variable. We can talk also about the joint distribution. This is a joint distribution over 2 variables that you see here, MW and Amax. I took the picture from somewhere. This is the source. It doesn't matter what it is, where it is from. You can imagine joint distributions in 2 dimensions at least as almost like a geographic map that shows you where the combinations of variables that are most likely are. Joint distributions are expressing essentially probability distribution over multiple variables. And they are much more interesting than distributions over single variables. What's the reason for that? The reason is that if you have a joint distribution, then given the value of some of the variables in the joint distribution, you can estimate the probability distributions over the remaining variables. So if I have a joint probability distribution over the amount of time that students spend on a course and the grades in the course, 2 variables distributed jointly, you probably suspect that there's going to be a strong dependence between them. Those students who spend more time will generally have higher grades. Again, this is uncertain. There may be somebody who spends very little time and gets a good grade, and somebody who spends a lot of time gets a poor grade. But overall, there's going to be a dependence. And if you have the joint distribution, you can predict, with uncertainty of course, what grade a student will get given that she works so and so many hours on the course. So very interesting, very useful property. Pictorial representation of a very simple case is a plot known as scatter plot. Scatter plots show you points. Every point corresponds to a record in the data for 2 variables. So you have 2 variables, and every point represents 2 values, the values of those 2 variables. When you look at scatter plots, you can see how those variables are jointly distributed roughly. For example, in this plot, you see that there is a dependence, maybe not necessarily linear, maybe somewhat curved, but those two variables are dependent. Higher values of one imply higher values of the other. Statisticians draw regression lines, can be linear, non-linear, which are useful because when you have a regression line, you have a formula from one value of one variable, you can predict the other, or distribution of the other. Now, what is Bayesian probability theory? Bayesian probability theory is essentially a theory that originates from a theorem, from a paper published after his death by a Reverend Thomas Bayes, an 18th century amateur mathematician, a reverend, a priest, who wrote essentially two papers. One of them was published during his life. The second, he was unsure. It's not like today that scientists try to publish as much as possible. He was a very modest fellow, brilliant. His wife found the scribbles in his desk and gave it to a friend. The friend read it and found it beautifully ingenious. So what did he write in that paper? He proposed a theorem that was very easy to prove. Each one of you would prove it as a homework in 5 minutes, probably, if you got a hint. From the definition of conditional probability, you must have seen that. This is not something new for you. A conditional on B and B conditional on A. What you see is that the probability of A and B jointly is on the right-hand side. So if you multiply the first equation, both sides, by probability of B, the second by probability of A, you will get on the right-hand side probability of A and B jointly. Then the left-hand side should be equal. You transform the equation and get a formula that is known as Bayes' theorem. Nothing unusual, very easy to prove, so you could say, well, what's the deal? The deal is actually in the interpretation. Reverend Bayes, in his paper, wrote that this formula gives us a way of changing our opinion in light of evidence. If you look at this element, it's the probability a priori of an event A. If you look at the event on the left-hand side, it's a probability of A conditional on B. What does it mean, conditional on B? I have observed B, and now I'm asking the question, what is the probability of A now that I know that B is true? An example, I'm looking out of my window now and see there is a person in a distance, 300 meters. I have my age already, I can't see that well. So I wonder myself, is this a woman or a man? Probability that it's a woman in our cultures is roughly 50-50. There are just as many women walking in the street as men. So now I look more carefully and I see that I see long hair. There's a little bit of a wind and I see long hair, blowing in the wind around the head of that person. So now I know that the person has long hair. Now, what is the probability that this person is a woman now that I see long hair? Of course, it's uncertain because we have men with long hair, we have women with short hair. So it's uncertain. But the formula gives us a way of calculating the probability after seeing the long hair. These two elements are just things that describe how strong is this evidence in testifying that this is a woman. Consists of the two elements. We will see that on an example in a moment. So we have a mechanism for changing our opinion in light of new evidence. A numerical example, until 1980s, I believe, in Pennsylvania, in US, there was a mandatory test for venereal diseases before you get a marriage license. So if you want to get married, you go to the town hall, you ask for a certificate, for marriage, that you have never been married before, and before they give you the certificate, they ask you, why don't you go to that lab, pick any lab, and undergo a syphilis test. That's a way of protecting the other person from potentially venereal disease. So let's assume that the probability of a young person wanting to get married having the disease is very low, 1 in 1,000. And these are the parameters of the medical test. They are very good, very, very good actually. Sensitivity is the ability of the test to detect syphilis, 98%, close to being perfect. Specificity is the probability that a healthy person will test negatively, also quite high. So now our fiancé comes back from the doctor, looks kind of funny, smiling, and says, well, look, I have a positive test result. Now, what is the probability that our fiancé actually has syphilis? The probability a priori was 1 in 1,000, and now we have a positive test. Here is Bayes' theorem applied to that case. As you see, very similar to what you saw on the previous slide. Probability of seeing a positive test at all is calculated by so-called theorem of total probability. Very, very easy to understand. If you want to calculate the probability of any event, you can introduce another variable and then go through all the possible states of that variable. In this case, there is S and not S, syphilis and no syphilis. Calculate the conditional probability and weigh it by the probability of that state. Very easy to understand. We do that, we substitute the numbers. This is the a priori probability of syphilis in that fiancé. We use the formula, we calculate, and the posterior comes to be around 2%. I chose this example on purpose to show you two things. One is that you can do it and calculate it, and I guarantee you that this is a correct calculation. As long as the numbers that we got in the description of the problem are correct, this is a correct calculation. The second reason is I wanted to show you that probabilistic inference is very often counterintuitive. Most people, when I'm in a classroom, most students believe that the posterior is very high. Given such high parameters of the test, the posterior should be very high. So it's counterintuitive. That tells us that when we do anything with it, we should pay attention to the user interface to make sure that people understand and accept the results. I'll show you another explanation of the same problem, which hopefully is more intuitive. This is a picture showing us a population of 10,000 individuals. There are 10,000 small squares in this picture. The people who are sick, who have syphilis, is 1 in 1,000. That's 10 people will be sick in that population. So now let us screen the whole population. Let's do a test on all of them. What will we see? First of all the sick people will test positively with the sensitivity of 98%. 9.8 of those people will test positively, which means 10 people, right? We need to round here. They will all be detected by the test. Very good test, very good sensitivity. On the other hand, the specificity is not that great. It's 95%. Actually, it's quite good for a medical test, but it misses some people. In other words, it assigns them false positive result. 5% of the people will test positively falsely. And that's roughly 500 people. So now, how many people among those who tested positive are sick? That's roughly 10 out of 500, which is 2%. You see the more intuitive, hopefully, explanation of what was happening here, what is happening here. It's Bayes' theorem in action, just another way of applying it, doing this, changing our opinion in light of evidence. Reverend Bayes they say that the picture couldn't be of their reverend base because in the 18th century, all priests wore wigs, and this guy looks like doesn't have a wig. But everybody uses that picture, and I think they even put that picture on his grave. They found his grave after realizing how important that publication was. If you want to have a gentle introduction to Bayesian inference, I recommend a book by Sharon Verse McGrain with a very long title, or if you have just an hour, you need more than 1 hour to read the book, watch her talk at Google on the following video. Very nice, very enjoyable talk telling you the history of Bayesian approach to probability. It works. It's reliable, solves hard problems. If you look at the title, many things that where Bayesian theory was used. If you watch the movie Imitation Game about Alan Turing, you realize that he actually used Bayesian approach. I don't know if he was doing it consciously or not. There's a scene in the movie where he runs out of the bar to the lab when he realized that he needs to use he needs to look for the code in the right places, which is precisely using Bayesian approach, the prior probability distribution of different possible codes. What's the difference between Bayesian and classical approach? You've used classical for sure in your risk analysis, in the things that you're doing. The main difference is in the definition of probability. In the paper by Bayes, he writes about it in such a way that we could interpret the probability, the prior probability, as a subjective measure of belief. So now, when you ask a statistician, what is the probability of a nuclear war? A classical statistician will say, sorry, it's a very bad question. I cannot answer it because probability is a limiting frequency. That's the definition of classical probability. So I have no clue. A nuclear war, I cannot even imagine it to be a repetitive process, so I cannot tell you. A Bayesian will have no problem with telling you 0.24, 0.55, 0.01, can produce a number because that number will be a measure of personal belief. Each one of you, in fact, can give me that probability if I sit down with you, offer you a coffee or a bottle of beer. You can probably, after some time, give me that probability. The relation between classical and Bayesian, it took 100 years for the Bayesian approach to be accepted. I suspect more than half, majority of statisticians are now using Bayesian approach. Classical statisticians will accuse Bayesians of doing hocus pocus, the prior. It reminds us of the 1960s when the very bad, ridiculous idea came up and got accepted in the society that there are many truths, that two people, one says yes, the other says no, and they both can be right. That's, of course, a logically ridiculous idea. So they say, well, in Bayesian approach, anybody can have his or her prior and fine. Luckily, it's not that bad. You can have your prior, but there are so-called limit theorems telling you that as long as your prior is not weird, your prior can be weird, like 0 is a weird prior, or infinitesimally small number is also a weird prior. As long as it's a reasonable prior, you will, by updating it based on your observations, you'll get to the posterior that is the same that a frequentist would have given data. So it's not as bad. And you can do, the big advantage is that you can do useful work when there are no data at all. That's the big thing about Bayesian approach. If you have no data, or you have data over some variables and not others, you can still do useful work.